Hi, it's ChemGal, and today we're going to talk about resonance. But before we do, you must have a good understanding of formal charge. If you're a bit fuzzy on this topic, feel free to watch my formal charge video linked down below. So here you have what looks like two different structures. These are structurally a bit different, where here you have a double bond and here you have a single bond. But what if I told you that these were actually the same compound and that they look different because there are electrons flowing around the compound? It's kind of like you. You wear different outfits every day, but you're still you. And so this compound can exist in different forms, but it's still the same compound. And we call that resonance. To indicate that these are resonance structures of the same compound, we put a double-headed arrow in between them and brackets to surround them, like this. Now, to show that this compound turned into this compound, we have to draw an arrow. And so what we want to show is that this bond here broke off in the form of a lone pair and jumped onto the nitrogen. And this makes sense, right? Because you know that every single bond contains 2 electrons. So if we take one of these bonds and break them, we can turn them into a lone pair and put them onto the nitrogen. And that corresponds to the new lone pair that you see here on the nitrogen on the right. So to show this, we draw an arrow going from the bond over to the nitrogen. And this indicates that the bond here is going to break and form a lone pair on the nitrogen here. Now notice here in the beginning how the nitrogen was positively charged and the carbon here was neutral, whereas in the end this nitrogen here was neutral and the carbon was positively charged. Why did that happen? If we quickly look at this nitrogen over here and we calculate its formal charge is equal to valence electrons minus surrounding electrons, and nitrogen has 5 valence electrons. Surrounding it right now are 4 bonds, and so there's 1 electron from each bond. So we have 5 minus 4, which makes a total of positive 1. And so that's why this nitrogen here has a positive charge. And if we look to the nitrogen on the right and we calculate its formal charge, we see here that it's going to be 5 valence electrons, and surrounding it right now, it's going to be 1 from each bond and 2 from the lone pair, which makes for a total of 5 surrounding electrons. And 5 minus 5 is 0. So that's why that nitrogen becomes neutral. Now if we look to the carbon in the beginning, we see here that it actually is going to lose a bond. So initially it had 4 bonds, 1, 2, 3, 4. And we know that carbon is happy when it has 4 bonds. But if we look to the right, we see that this carbon only has 3 bonds because it lost one of the bonds when making this new resonance structure. And so a carbon with 3 bonds is a carbocation because it's missing a bond. And so that gives it a positive charge here. Even if we wanted to recalculate its formal charge, it's equal to valence electrons minus surrounding electrons. Carbon has 4 valence electrons and surrounding it right now is 1 from each bond. Because it has 3 bonds, it has 3 surrounding electrons, and that makes for a total charge of positive 1. So you see here that this positively charged carbon is valid. So one more thing I want to point out before we begin is that there's always a conservation of charge. So notice here in the beginning how our structure was positively charged. And when we drew a new resonance structure, it was also positively charged. It's just that the charge moved. And so we always have that conservation of charge. So there's a few rules to this resonance game. In the last example, we transformed a bond into a lone pair. But you can also transfer a lone pair into a bond and a bond into another bond. So let's go ahead and give that a try. And so in this example, we have to draw all possible resonance structures for this compound. So you just learned how to turn a bond into a lone pair. Is there a place where we can do that here? We see that over here, we can turn one of these bonds into a lone pair on this oxygen atom. Let's go ahead and draw what that resonance structure might look like. And so now I have drawn here the structure. And remember that we took a bond away from the oxygen atom, so we have to make this a single bond. And now how many lone pairs is this oxygen atom going to have? It started off here with 2, but what happened was it gained 1 from the breakage of that bond. So now it has 3 lone pairs in total, or 6 surrounding electrons. Now what does that mean for that oxygen atom? What kind of charge is it going to bear? Well, if we calculate its formal charge, it's going to equal to valence electrons minus surrounding electrons. This oxygen has 6 valence electrons, and surrounding it right now there's 1, 2, 3, 4, 5, 6, and 1 from the bond, which makes for a total of 7 surrounding electrons. Therefore, its charge is 6 minus 7, which is a negative 1. So now we have to reassign the charge as a negative charge here on this oxygen atom. And if we're looking at the beginning and in our second structure, we notice that the charges are not the same. So we see here that we're neutral, and here we have a negative charge. That means something is wrong. That means that there's definitely another atom here that also bears a charge, because if this first structure is neutral, this one also has to have a net charge of 0. And so then we begin to recognize that when we remove this double bond here, we're not only affecting the oxygen atom, but we're also affecting this carbon, right? We took away one of its bonds. And so if we look to the carbon now, we see that it only has 3 bonds. So in the beginning it had 4, but now it only has 3. And so that means that that carbon is going to bear a positive charge, because 4 minus 3 is positive 1. And so in this example, we saw how to convert a bond into a lone pair. Now, how can we convert a bond to a bond? Well, we see here that we have this double bond. And so we see that this carbon here is positively charged, which means it's missing a bond. And so what we can do is take the bond from over here and bring it in between these 2 carbons. Let's go ahead and see what that might look like. And so now we see that we got to remove the bond from here and place it over here. So what does that mean for this carbon? So here our carbon only had 3 bonds and it was a carbocation, but now this carbon has 4 bonds, and that means it's neutral. So what other atoms did we manipulate here? And so if we took the bond from here and threw it over here, we not only affected this carbon, but we also affected this carbon. And you might be asking, well, what about the middle carbon? And so technically we took away the bond from the middle carbon initially, but we still gave it back to the middle carbon when we put it over here. So nothing really changed for this middle guy over here. This carbon was attached via 4 bonds in the beginning, and it was attached to 4 bonds in the end. And so who did we take the bond away from? We took it away from this carbon. So initially this carbon had 4 bonds, but now it only has 3. So what does that mean for this carbon? What kind of charge is it going to bear? It's going to bear a positive charge, since it only has 3 bonds. And so now you see an example of how to transfer one bond to another bond, where we took this bond over here and transferred him over here. And let's go ahead and draw the arrow for that. So now you might be noticing some things you can't do. So for instance, we can't transfer a lone pair from one atom to another atom. It doesn't work that way. We also can't break the octet rule. And lastly, we cannot transfer electrons or a bond to a non-adjacent atom. If you're ever moving electrons or a bond, it always has to be to an adjacent atom. And so take a moment to pause the video and try this one on your own. So we now know that we can turn this bond into a lone pair here. And if we do that, we can see that the next structure is going to look like this, where we got to erase this bond here and draw it in the form of a lone pair. And why did that happen? That was because this bond broke off here and turned into a lone pair on this oxygen atom. But that's not the only atom that we affected. So when we took this bond away from here, we not only affected the oxygen, but this carbon as well, since we took a bond away from it. So we see that this carbon originally had 4 bonds where it was happy, but now it only has 3. That means it's a carbocation. And so it bears a positive charge. And so what's the charge going to be for this oxygen atom here? We can recalculate that by saying that formal charge is equal to valence electrons minus surrounding electrons, where oxygen has 6 valence electrons, and surrounding it right now is 1, 2, 3, 4, 5, 6, and 1 from the bond, makes for a total of 7. 6 minus 7 is negative 1. And so we see that this oxygen atom here is going to bear a negative 1 charge. Wow, that's a lot of charges. We'll talk about that in a second. And so now we see that we can also transfer this lone pair to this bond here. And if we do that, what is the structure going to look like? So if we do that, we're definitely going to have to erase one of the lone pairs on the oxygen since we're using that to form a bond. And now we got to reassign the charges, so I'm also going to erase that positive charge here, right? The area that we manipulated was between this carbon and this oxygen, so we got to go ahead and recalculate the formal charges for both of those. So where this carbon originally had 3 bonds and was a carbocation, now it actually has 4. And so what does that mean? This carbon is happy because it has 4 bonds, and so it is neutral. And what about this oxygen atom? It originally had 3 lone pairs, but it used one of its lone pairs to form that new bond. And so now it only has 2 lone pairs. So if we calculate the formal charge for it, formal charge is equal to valence electrons minus surrounding electrons. Oxygen has 6 valence electrons, and surrounding it right now is 1, 2, 3, 4 from the lone pairs, and 1 from each bond here. And so that makes for a total of 6 surrounding electrons. 6 minus 6 makes for a total charge of 0. And so we see here that now this oxygen is neutral and this carbon is neutral. And so if we wanted to check for the conservation of charge, we see that here we started off with a negative net charge. Here we also have a net negative charge. And here we have a net negative charge. So this looks pretty accurate. But now there's something else I want to talk to you about. So remember how I said that resonance structures are like how you wear different outfits every day, but you're still you? And this compound exists in different resonance structures, but it's still the same compound? Well, don't you ever have days where you wear something that you don't like very much? And so maybe you have your least favorite outfit. And so maybe you spend less time wearing that outfit. And so resonance structures act kind of the same way. So if a compound has a least favorite structure, it'll spend the least time in it. And we call that the least contributing structure. And how do we know if a structure is the least contributing structure? So we might look for something called an increased separation of charge. So if we have too many charges on a structure, that could mean that it's very unstable. And so the compound doesn't like to sit in that structure very often. And so which one of these structures might you think is the least contributing structure? That would most likely be structure number 2. And that's because structure number 2 has an increased separation of charge, where we have 3 separate adjacent charges here, and that's very unstable. So this would be the least contributing structure. And so if someone told you to draw the resonance structures for this compound, you might first think to bring this bond in the form of a lone pair here. And while that may look all great and dandy at first, we gotta remember that this carbon here is actually bonded to 4 things. It has a hydrogen here that we don't see, and I have that highlighted in their expanded form. So if we were theoretically to, let's say, bring a lone pair down over here, what might that look like? And so over here, we would get rid of that negative charge. And so over here, we would get rid of that negative charge, and we would also get rid of a lone pair since we used it to form the bond. Likewise, over here, we would get rid of the negative charge and the lone pair since we used it to form a bond. And so now we see that we have formed a double bond here. And so in bond line form, all things might look swell because we don't draw in those hydrogens over there. But we gotta remember that this carbon is still attached to a hydrogen. And we actually see that here in the expanded form. Now we see that this carbon is bonded via 5 bonds. 1, 2, 3, 4, 5. And so we broke the octet rule. And this is a big no-no in organic chemistry. And so that's just something I want you to keep in mind. Whenever you transfer electrons to neighboring atoms, you want to make sure you don't break their octet rule. So this is something you can't do. And so now here, I have drawn in all these resonance structures for different compounds, and I want you to take a moment to draw in the arrows for each of these resonance structures. Alrighty, let's get started. So in the first example, we see here that the difference between the first structure and the second structure is that one of the bonds moved. And we can see that this bond over here, which was a double bond, became a single bond. And this bond here was a single bond and became a double bond. So we can make the assumption that one bond transferred over here. And we can draw the arrow for that. And so you might be wondering about that charge. So if we go ahead and draw in some hydrogen atoms here, we know that this carbon here has a hydrogen atom, and this carbon here has two. Because remember, this guy is positively charged, which means it can only have 3 bonds. So if it's already bonded to this carbon, it can only have 2 other bonds to hydrogen. So let's draw those in for the second structure. Remember that the amount of hydrogens on carbon atoms never changes when drawing resonance structures. And so now we see here that this carbon started off with 4 bonds, but now it only has 3. And so that's why this carbon became positively charged. Likewise, this carbon atom here had 3 bonds and was a carbocation, but gained a bond, and so now it has 4. And so that's why it became neutral in this resonance structure. Now let's examine the second example. Here we have a double bond, which became a single bond, and here we have a single bond, which became a double bond. So we can make the assumption that this bond transferred over here. And so that's how you're going to draw the arrows for this set of resonance structures. Now on to example number 2. This carbon over here has a lone pair, and it somewhat gets confusing for students to imagine this. So whenever this carbon here has a lone pair, you can draw in its hydrogens to make it make sense. So we can move this lone pair over to the side and draw in this carbon's hydrogens. So it has one hydrogen right over here. And so what makes it negatively charged is that this carbon has 3 bonds and a lone pair. And if we calculate the formal charge for that, carbon has 4 valence electrons, and surrounding it right now is 1 from each bond, which is 3, and 2 from the lone pair, which makes 5. 4 minus 5 makes a -1 charge on that carbon. And so we also call that a carb anion, which just means negatively charged carbon. So don't be freaked out if you see that next time. So we see here that this carb anion is going to become neutral, and that this carbon is going to become a carb anion. And so how might we draw the arrows for this? And so initially you might be thinking that this guy's a single bond and becomes a double bond, and this guy's a double bond and becomes a single bond. So you might be thinking that this bond is going to transfer over here, but that's not what happens. And so that's why these examples get a little bit tricky. What actually happens here is this lone pair becomes a bond between these two carbons, and this bond breaks off and turns into a lone pair onto this carbon. So this bond here, you can imagine it breaking off in the form of a lone pair and traveling onto this carbon over here. So take a moment to make sure you understand that. Now what about this last example? So we see here that this double bond is becoming a single bond, and that this oxygen is gaining a lone pair. So we know that we can draw an arrow going from this bond to the oxygen atom. And so what's going to happen in the second example? Here we have a single bond turning into a double bond, and we have this oxygen atom losing a lone pair. And so we can say that one of its lone pairs is going to form this new bond over here. And so that's the new bond that we see forming over here. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!